Okay, we are doing another math review, and hopefully my computer doesn't go crazy in the middle like it likes to do. It looked like it started there for a second. Okay, this is the thumbnail for the video, so you get to be here for that. Hooray. Okay, so we're doing another math review. All right, let's get rid of this. The first thing we want to do is I wanted to show you transfer function. This is a very simple formula. By the way, while I draw this out, I want to let you know there is an exam covering modules 1 and 2, and it's going to open today right after I put this up. It's going to be open for a week, so it's going to be due the same time that module 3 is. And unlike other exams, if you've been in classes with me before, I am going to allow you to use a page of notes, front and back. And that's because there's a heck of a lot of formulas on this portion of the test. And there are for all of these modules, and I don't want to test you over your ability to memorize formulas. I want to test you over your ability to use them when you have access to them. So basically, one thing I want you to make sure that you put on your page of notes is everything that we've gone over in these two math reviews. Make sure that you have the functions and make sure that you know how to use them. Like maybe put a sample problem from the quizzes or something, or from our math review, so you know how to use the figures that I'll give you during the exam. Of course, there's going to be conceptual stuff on there as well, and you guys are probably doing excellent with the conceptual stuff. When I look at the scores on the quizzes, you're doing great. So I don't think you're going to have trouble with I don't think you're going to have trouble with the conceptual stuff. All right. So the transfer function is going to use h, y, and x. H is the filter, y is the output, x is the input. The formula can be written h of f equals y of f over x of f. It can also be written, so that means that the filter equals the output over the input, but usually we don't know the output, so that's kind of ridiculous to have it, we compute the filter based on the output and the input. Sometimes we do. Sometimes we know what we're putting in, and then we can measure what we're getting out, and then we want to decide and try to work backwards and figure out what the filter was. But sometimes, a lot of time, what you're going to have is you want to know what the output will be, and you're given the filter and the input. So you just multiply your input. This is the frequency. So the frequency in question. You could do this for every frequency in your signal if you wanted to. I mean, usually this is why we use the programs like Prot and Audacity, is because we don't want to do this by hand for every frequency. But you could. So f is the frequency in question. It should have a little sub n by it, just meaning that you're going to do it for every frequency in question. So if your filter was attenuating, so let's say your filter looks like this. This is the filter. And this is 600 hertz. Let's say that 1 amplitude is right here. And so let's say that up here at 600 hertz, this coming across is 1.2, and at 500 hertz, it's 1, and at 400 hertz, it's I don't know, that looks like 0.5 to me. Okay, so there's the filter. Now the input is just going to be, let's draw a box around this. The input is just going to be all 3 frequencies, and they're all an amplitude of 1. So this is going to be a 400 hertz, a 500 hertz, and a 600 hertz tone. That's the input. So then all you do is you multiply the input by the filter. So 6 times 1.2 is, well, sorry, not 6. We're going to multiply the amplitude, which we know is 1 for all of these. I should say that, 1. So 1 times 1.2 is 1.2. Cool. 1 times 1 is 1, and 1 times 0.5 is 0.5. And so now our signal is going to look like our filter. And so we'll have 0.5, 1, and 1.2. So the filter has this whole, range. It's doing things to every frequency. Our input only has these 3 frequencies. And so then our output is only going to have those 3 frequencies. It doesn't matter what this envelope looks like for the filter. It's there, but we've only got these 3 frequencies. So all we're going to get out are these 3 frequencies. But it has the shape of the filter that we put in. So there's the transfer function. That's very simple. Just multiplying things. Man, the bad thing about deleting all this is I've got all these dots now that I've made, and those are hard to erase. Okay. But it is really great that all I have to do is touch the line and it gets erased. Okay, good enough. Next thing, we want to look at mass spring resonance. Cool. So our function is F. This is my italicized F. Maybe it should have a bigger, there we go. So the resonant frequency, that should be an R, even though it doesn't look like it, equals 1 over 2 pi times the square root of Km. Remember that K is stiffness, M is mass. Sorry, this is K over M. M is mass. Okay, so 1 over 2 pi multiplied by the square root of K over M. One of the questions that you might have seen in the quiz or in one of the knowledge checks says that stiffness is increased by a factor of 9. So stiffness is increased by a factor of 9. What this means is, I think I'm going to run out of room. That's one of the things it means. But what this means is that, so now your resonant frequency, let's call it R1. Actually, let's call it R2. This is now R1. So your resonant frequency, now that it's increased by a factor of 9, is going to be 1 over 2 pi, it's like before, multiplied by the square root of 9k over m. Now, you could go all the way through this and figure some stuff out and cancel things out, because what you're going to want to do is you're going to want to treat this like you want to solve for the equation for FR2 to make it look like FR1, and then you're going to have a number left over. So one other piece of information you get about this is that FR1 is 150 hertz. So we know that 150 hertz is this formula here. We're not given any information about K or M. We're just told that your first resonant frequency is 150. Now stiffness is increased by a factor of 9. What is the new resonant frequency? So again, we don't have any information about K or M. So it's not like we can solve for K and then solve for M and put this in and then just multiply it by 9. We can't do that. What we need to do is solve for FR1. So the way that you do that, I'm going to pull some stuff out of your memory here. If you have a square root in an equation, you can break these into, you can break them into 3 different things. So if you have 9 times K divided by M, those are it's a multiplicative thing, or division, which is just multiplying by the inverse. But you could break this into the square root of 9 times the square root of K times the square root of 1 over M. It's the same thing. Oh, that's right, I can write off the page. That's great. So these are equivalent. It's the same thing. So what you're going to want to do, let me erase some. No, I've got enough room. We're just going to try to squeeze it in. So what you're going to want to do is rewrite FR2 as 1 over 2 pi, that can stay, multiplied by the square root of K over M, that can all stay, multiplied by the square root of 9. We're just pulling that out. The square root has to stay around it though. It doesn't get to run off scot-free. It still has to be, the root has to be taken of it. But now you should see something familiar here. This is this, which means it's this. So this portion right here is FR1, which means that's 150. So you can then rewrite this as FR2 equals 150 times the square root of 9. Well, the square root of 9 is 3, so it's 150 times 3, which means it's 450. That's your new frequency, 450. Cool. So you could do all that. You certainly could. I mean, that's like the proof version, right? The long version where you make sure that all the math is correct. But there's always a shortcut. And the shortcut, if you get a question like this, is what I'm going to show you. As soon as I erase all this, there's a way to just erase everything. Okay. So the shortcut, FR1 equals 1 over 2 pi times the square root of K over M. And now we want to increase K by 9, by a factor of 9, not just by 9. So we're multiplying K by 9. So anytime you see that K is being increased, well, all that means is you're going to take your first frequency, which is 150, times, get rid of all this stuff, times what's added, the square root of what's added. So if it's K, you're going to multiply your frequency by the square root of 9. Now what if we increased M by a factor of 9? Well, it's kind of the same thing. if we increase m by a factor of 9, then what we do is we take our base frequency, 150, multiplied by square root of 1 over 9. That's what we've pulled out. Well, the square root of 1 over 9 is 1 over 3. Another way to write that is just 150 over 3. So if you increase k by a factor of 9, it's 450. And if you increase m by a factor of 9, it's 50. Cool. Okay, let's move on. The next thing is a Helmholtz resonator. All right, so a Helmholtz resonator. Maybe, I think maybe the problem is I write my titles way too large. A Helmholtz resonator. How many resonant frequencies does a Helmholtz resonator have? It only has one resonant frequency, just one. That's important. Why is that important? Because if you were going to look at a plot of a Helmholtz resonator, it'd look like this. This is where its resonant frequency is. That's it. Okay, so that was my couch, by the way. Our formula for a Helmholtz resonator is FR equals C over 2 pi multiplied by the square root of A over VL. Here's a Helmholtz resonator. The area is the area of this opening right here. The volume is the volume of this chamber down here. And the length is the length of that neck right there. All right. So, how do you solve? Well, one of the questions that we were faced with was, your resonant frequency equals 100 hertz. The opening is increased by 4, a factor of 4. What does that do to the frequency? Well, what is the opening? It's A, area. So this is a lot like the last one that we did. A lot like our mass spring resonance, right? So we have F1 is 100. And what's changing here is that there's going to be a 4 up here by the A. Well, it can come out. You're going to rewrite it as, let's make a little box where we're doing a rewrite. You're going to rewrite it as C over 2 pi multiplied by the square root of 2 multiplied by the square root of A over VL. Now we can get rid of all of this stuff. We're left with the square root of, whoops, sorry about that. I'm getting ahead of myself. Not the square root of 2, it's the square root of 4, which is 2. So openings increased by 4, so 4 is multiplied by A. This is increased by a factor of 4, I should say, not by 4. So 4A, we've pulled the 4 out of that square root portion. Just make sure I'm still recording here. Yes. pulled the 4 out of the portion, out of that portion, the square root of 4, so that's there. We can get rid of the parts of the equation that are standard. Now we have square root of 4. Well, like I said, square root of 4 is 2. So now we have our new frequency, f2, equals our old frequency multiplied by 2. So our new frequency is 200. Cool. I think I have another question that I want to run through with that. I mean, this is one type of question. What happens if we just change some things? All right, let's rewrite our equation. Fr equals c over 2 pi multiplied by the square root of a over v L. Okay. So I have this question here that I want to run through. The area is 100. Well, let's make this small for a second. All right. The area is 100. The volume is 6,400. The length is 100. And the speed of sound is 340,000. Now, if you're wondering, I mean, I'm sure you've probably guessed why. The reason why sometimes the speed of sound is 340,000 and why other times it's 340 is because we're changing our base. In this case, we're using millimeters for all of these. Millimeters squared, millimeters, and millimeters cubed. And here we're using millimeters per second. When we use 340, then we're using meters. Okay, so we solve this. You just, work it through. And you can also use a calculator on the exam, by the way. So what you do is you just rewrite your formula, Fr equals 340,000 over 2 pi multiplied by square root of 100 divided by 6,400 times 100. All right. Now, you could put this in your calculator, and if you want to put it in your calculator and do it that way, do it. If you don't, there's definitely some simplification that we can do. So we can rewrite this as Fr equals 170,000 over pi multiplied by, I'm going to stop writing at a slant, 175,000 multiplied by 10 over 80 times 10. Well, these 10s are going to cross out. This 80 is going to move under here by the pi. So then you can rewrite it as Fr equals 170,000 over 80 pi. Now you can remove 1 0 from both of those. So it's 17,000 over 8 pi. And now you can, divide by 2 if you want to. And you can make it 8,500 over 4 pi. And you can turn that into 4,250 over 2 pi. And you can turn that into 2,125 over pi. And there you're going to have to use your calculator. 2,125 over pi is, I don't have my calculator next to me. So my computer likes to stop recording when I switch applications for, cool reasons. Anyway, so I've been through all of this once, and then I just realized that it stopped once I brought up my calculator. So 21, what was it? 2125 over pi is where I ended for you guys. 2125 over pi is 676.8, I think, if I'm remembering it correctly. So it's 676.8 hertz is the resonant frequency for that Helmholtz resonator. If you were going to look at it on a graph, the filter for that resonator would be this, with the center frequency at 676.8 hertz. Why? Because a Helmholtz resonator only has one resonant frequency. If you had another peak over here, this would be like a big no-no. There's only one resonant frequency for a Helmholtz resonator. All right, so let's get rid of this. Boop. Now we're going to do 2 open ends tube. Hooray. The frequency for a tube that has both ends open is FRN. The little n is there to denote that there are multiple resonant frequencies, not just one, equals n multiplied by C over 2L. Okay, so in this case, n is going to be the resonant frequency you want, res freq. C is sound, which in this case is always going to end up being 340. So you can just, I'll say that in the exam, but you can just take that as what it's going to be. And then L is the length of the tube. Okay, so let's say that we have just like a stupidly long tube, like a 2-meter long tube. This is like a 6-foot tube. I don't know why anyone would have that, but we want to find the first resonant frequency for a 2-meter tube. Again, it's stupid, but anyway, so FR1 equals 1, because our n is 1, so we want to find the first resonant frequency, 340, speed of sound, over 2 times 2, that's the length of our tube. All right, well, we can start reducing some things. So we know that 1 times anything is itself, so we can just get rid of the 1. And now we're ending up with 340 over 4. That can be reduced to 170 over 2, which can be reduced to 85. So 85 hertz is the first resonant frequency. Great. Well, what if we want to find the second resonant frequency? We can do that too. If we want to find the second resonant frequency, this isn't going to change. That's all the same. What's going to change is this, the n. So for the second resonant frequency, FR2, we're going to have 2 times 340 over 2 multiplied by 2. Well, we already know that 340 over 2 multiplied by 2 is 85. So we can rewrite this as 2 times 85, and 85 times 2 is 170. So our second resonant frequency is 170 hertz. if I asked you to compute that, and then I asked you as a second question, what does a graph of this look like? Let's just get rid of all this ridiculousness. Oh, I guess I could have kept two open ends too, whatever. So a graph of that, of the first two resonant frequencies, would look like this, with the first center frequency at 85 and the second resonant frequency at 170. So that would be the correct answer. I might ask you to compute 3 or 4, but then you'd have numbers for those as well. And it looks different from a Helmholtz resonator because a Helmholtz resonator only has a single resonant frequency. So now we're going to do a one closed end tube. My handwriting, like, I want to say that it's bad because I'm writing on a tablet with a little stylus, but I have a feeling that it's like this pretty much all the time. So this formula is going to be FR1, FRN actually. FRN equals 2N minus 1 multiplied by C over 4L this time. Everything is the same. N is the resonant frequency you want to find. C is the speed of sound, which is 340 in this case, and L is the length of the tube. So let's say that we closed off one end of the tube. We turned it into like a clarinet. And now we want to figure out how have the resonant frequencies changed. So the length of our tube is still 2 meters, but now we have to use the formula for a closed end tube. All right. So we want to do the first resonant frequency for a 2-meter tube again. So let's rewrite our formula. FR1 equals, and we're going to have to add some brackets, 2 times 1 minus 1 multiplied by 340 over 4 times 2. Okay, so we can simplify 2 times 1 is 2, 2 minus 1 is 1, so we're left with 1 times 340 over 8. 4 times 2 is 8. 1 times anything is itself, so we're left with 340 over 8, and we can start to reduce, so we've got 170 over 4, or 85 over 2, or 42.5 is our answer. 42.5 hertz. Great. Okay, so 42.5 hertz. Now remember, like last time, I showed you that if you want to compute the second resonant frequency, once you've already done the first, this part isn't going to change. And that's true here too. So let's say now we want to do the second resonant frequency. Well, all we have to do is FR2 equals, you know what, let's do this in a different color because I'm switching what I'm doing. FR2 equals, some brackets again, 2 times 2 minus 1 multiplied by, and here we know that it's 42.5 because of last time. So now we can start reducing. 2 times 2 is 4, 4 minus 1 is 3, so this equals 3 times 42.5. 3 times 42.5, let's just do that up here in the margins. 42.5 times 3. That's 15, carry the 1, that's 6, add that, so it's 7, that's 7. 3 times 4 is 12, and then we need to move our decimal, so it's 127.5 equals 127.5 hertz. Okay, so our first resonant frequency is here, and our second resonant frequency is here. Again, if I ask you to look on a graph, you have this and this, 42.5 here, 127.5 here. Okay, so one last thing that I wanted to go over, which isn't exactly math, but it's kind of related to it, I suppose, is how frequency is going to change based on constriction. So some of you are a little confused by this, and I think rightly so, because a lot of the graphs that we were seeing from the textbook and other websites are showing graphs for both frequency and or for pressure and velocity. So once you get into your mind that you're looking at pressure, then they give you a graph for velocity and it gets a little confusing. So here's a tube with one closed end. Where's maximum pressure? Right here. Minimum pressure is here. So when you have a constriction at maximum pressure, your frequency goes up. When you have a constriction at your minimum pressure, your frequency goes down. So constriction here, frequency up. Constriction here, frequency down. On your exam, when I give you graphs with this, I am only going to ask you about pressure. Pressure only. I'm not going to give you graphs for velocity and pressure to confuse you. So I'm only going to ask you about pressure. Any graph I show you that's in a tube is going to be pressure only. I do want you to know that pressure and velocity have an inverse relation. So I want you to know that this is maximum pressure, but it also has minimum velocity. And that this has minimum pressure, but it also has maximum velocity. I want you to know that. But when I show you a graph, I'm only going to show you and ask you about pressure and how the relationship between pressure and frequency, what that relationship is. Okay, so your exam is going to be up soon. Good luck. And also, quiz 2 is open and fixed now, so if you want to retake it, you should. All right, I will talk to you later this week.